Hello guys and welcome to my 1K subscriber special. So this video is going to be really fun because we're not going to be solving any math problems, but what we are going to be doing is we're going to be ranking advanced integration methods on a tier list. So I just want to go ahead and thank everyone who has supported me on my journey. I mean, now I'm at 1,000 subscribers. I never thought I would reach more than maybe 100. I never planned to make this such a big thing, but it's been a great journey, and thank you all for all your support. So anyway, without any further ado, let's get right into the tier listing. So we're going to be covering 16 different advanced integration methods that I've used in my videos and one or two that I actually haven't used in my videos. And we're going to be ranking them on the standard S, A, B tier system, so with these possible ratings. I don't anticipate many Ds because all of these are very cool integration methods. So we're covering everything, pretty much anything past integration by parts, anything you wouldn't learn in a normal calculus class. But obviously we're not including like U sub and integration by parts and trigonometric substitutions or trig identities, stuff like that. So without any further ado, let's go ahead and jump right into the tier listing. So I'm going to go through every integration method and explain my choices one by one, and then at the end, we'll go ahead and just put the tier list up for everyone to see. If there's any integration methods that you don't recognize or you're not familiar with or you don't know how to use, I definitely suggest looking them up. I have some videos on some of them, and other ones you can just find on the internet, and you can learn something new today. So yeah, let's go ahead and jump right into the tier list. So we are starting off big with Ramanujan's master theorem. So this states that the integral from 0 to infinity of x to the s minus 1, also known as the Mellin transform of f of x, is equal to gamma of s times phi of s, as long as f of x equals the sum from n equals 0 to infinity of negative x to the n, phi of n over n factorial. So as you can see, this is clearly an incredibly powerful formula, and for that reason it's going to be really high up on the list. I'm not going to put it in S tier because unfortunately the Mellin transform doesn't show up all over the place. I mean, well, it does show up all over the place, but very often it's not possible to actually use this definition of f of x. So for that reason, I'm going to have to knock it down to A tier, but overall it's incredibly powerful. One thing that I don't like about it is it's difficult to understand why it works as opposed to some other integration methods, but it comes up in a lot of different situations. I believe I've used it in at least 3 different videos, so that's pretty nice. So this one's going to be an A tier for me. Again, if you haven't heard of this method, I definitely suggest going and checking out a video that I've made or that someone else has made and just learning how to use it, because it could come in handy. Anyway, let's move on to the next integration method. So the next integration method is actually the Mellin transform. So this is, you could argue that really this is covered by Ramanujan's master theorem or the other way around, but this is just taking the general case. So for many cases you'll be able to use the Mellin transform, but you won't necessarily be able to use Ramanujan's master theorem. So in most cases you are going to be able to use Ramanujan's master theorem, so the Mellin transform isn't the most useful thing in the world on it by itself. But there are many situations, like a recent video that I did, where you're able to work with a Mellin transform much more easily and do some limits and some manipulation. So for that, I'm going to have to give this one a B tier because it doesn't really show up all that much by itself, but when it does, it's incredibly helpful and incredibly powerful. It's also a one-to-one transform with an inverse transform formula, so that's also going to have to be a B tier for the Mellin transform. Next up, we have Glasswares' master theorem, which states that the integral from negative infinity to infinity of f of phi of x dx equals the integral from negative infinity to infinity of f of x dx, given that phi of x equals x minus the sum of ai over x minus bi. So essentially, x, you can replace x minus the sum of a bunch of 1 over x minus somethings when you're integrating from negative infinity to infinity. So it looks very niche, but if you play around with the definition of phi of x, there's actually a few different ways that you can use this. Most commonly, it's just going to be x minus 1 over x, which can help you solve a lot of nice integrals. including some rational integrals that would be otherwise very difficult. So overall, yeah, since it has applications to generalized integrals like rational integrals and not just specific cases, I'm going to have to bump this up. I was going to say B tier, but I'm going to have to put this in A tier just because it's useful for a lot of different general formulas, and it's incredibly powerful as well because with this theorem, this helps us do a lot of things that we wouldn't be able to do otherwise. So that's going to be an A tier for Glasser's master theorem. Again, if you haven't heard of this, I'd definitely go and check out some videos on the topic. And I just looked at my list, and now we are going to be taking a look at the Laplace transform. So the Laplace transform of a function of time is the integral from 0 to infinity of the function times e to the negative st dt. And this seems kind of random to those of you who aren't familiar with the Laplace transform, but for those of you who know what it is, you'll know that this is one of the most powerful tools for solving differential equations, but surprisingly also one of the most powerful tools for solving integrals. So for that reason, this is going to be our very first S tier, because this is just an absolutely incredible integration method. I mean, it pops up in all sorts of different integrals, and what's more is even when you don't see it pop up in integrals, chances are there's another way that you could have solved that integral using the Laplace transform, using limits. The great thing about the Laplace transform is there's lots of different rules that you can apply to it, and you can look up tables for the Laplace transform, which can help you evaluate the Laplace transform of almost anything and manipulate all sorts of things. And essentially, this is one of the best integration methods, I just have to say. That's why it's going in the S tier. It's super powerful. Absolutely, if you're not familiar with this, you should totally learn this right now. So that's our first S tier of our tier list. Let's go ahead and move on to the next method. Alright, so the next integration method is the Leibniz rule, which you guys probably know as Feynman integration. So the statement of this would be that the partial derivative with respect to some variable a of the integral of some function of x and a dx is the same as the integral of the derivative on the inside. Or actually, this one should not be a partial derivative right here. So the derivative with respect to a of some integral defined function is actually going to be the partial derivative on the inside of that function. And although this looks kind of random and not very useful, this is exactly the statement that allows us to use Feynman integration and all sorts of crazy different integration tricks related to Feynman integration and differentiating under the integral sign. So this is by far probably the most famous integration method, and honestly it is one of the most useful. But I know some of you guys are going to hate me for this, but I'm going to put this down not in S tier but in A tier. And the reason for that is when you're first starting out with integration, Feynman integration is absolutely your buddy because it makes everything so much easier, and it's honestly super easy to learn and to apply. But then what happens, at least what happened in my case, and I'm sure has happened with others, is you just learn Feynman integration and then you get stuck and you try to use Feynman integration on everything. And once I started working around that and I started realizing, okay, well, there's a way to solve this using Feynman integration and two other methods. Once I started trying those other methods, developed my brain better to be able to spot those other methods. So that meant when I went onto a problem where I couldn't use Feynman integration, I was actually able to solve it. So in a way, Feynman integration becomes sort of a crutch because it's just so useful and good in those early stages of integration. But once you get higher up, it's just a tool that you have to use, but you have to know that in some situations you're not going to be able to use it. So for that reason, I'm putting it in A tier because too often it sets people back when they're trying to learn how to do integration. But absolutely, it is an essential tool for any integration toolbox. So that's A tier. Let's go ahead on to the next integration method. As you guys can tell, I'm rating them all pretty high because I really like most of these methods. That's why I use them. But we will have some lower rated ones a little bit later. So next up, we have contour integration. So there's no real problem statement for this because contour integration can be used in a variety of different ways. So I'll just write contour integral of f of z dz. And this one, I mean, you guys know my opinion on contour integration, so I'm definitely going to have to put this in S tier. Complex numbers are just the natural way that numbers are supposed to be, and for that reason, contour integrals are incredibly easy to evaluate, just using the residue theorem. we only have to evaluate the limit of the function at a few points, and that tells us the entire integral, which, I mean, is just incredible, right? And, I mean, I counted all the videos and I came up with a number for all the different times I used the different integration method. I believe contour integration was either first or second with like 8 or 9 videos. And that just goes to show how many different applications it has and just how useful it is. So definitely an S tier for contour integration. And now we are going to have another S tier in here. I'm very sorry about making so many S tiers, but this is going to be the use of infinite series. And I'm not even going to specify power series because there are some infinite series that occur without power series, like expansions of sin h and cos, right? Or in hyperbolic tangent and hyperbolic secant. So infinite series are just so useful because in almost every situation you're going to be able to interchange the series and the integral, and so we can turn integrals of complex functions into just integrals of power functions using power series or other representations such as, for example, the diagamma function or something like that. We'll get to that later, but overall, power series just have so many different applications, and honestly, I feel like I use them in almost every single video, so definitely going to be an S tier for power series. Alright, let's go ahead and move on to the next method. Alright, so this next method is going to be the gamma and beta functions. So beta of alpha, and no, I shouldn't do that. Beta of A comma B and gamma of X. So the gamma function is defined by an integral t to the x minus 1 times e to the negative t, and it's an extension of the factorial function. The beta function is just a product of different gamma functions. So I've grouped these together because whenever you're using the beta function, you're also using the gamma function. So they're going to stick together for now. Now, I understand that the gamma function is essentially some sort of, it's just a tool in your toolbox. It's not necessarily a method that you're going to use. But I mean, it just pops up so often that I had to include it on this list. So really, we'll talk about the beta function being more of the integration method and the gamma function being more of just a general tool. So if we're just going to rate the beta function on this tier list, I'm going to have to give it a B tier. And the reason for that is, I mean, B tier is totally solid. There's nothing wrong with B tier. It's an absolutely very nice tool that comes up in lots of different situations, but it has such very specific definitions, so I mean you can only use it on a few different types of integrals, and it's not like something like power series or contour integration or Feynman integration where it's very dynamic and it applies to all sorts of different types of integrals. Again, it only applies to one, two, or three different classes of integrals. So for that reason, I'm going to give this a B tier. And next up, we're going to have the digamma and polygamma functions. So I'll just put the definition of the digamma function right here. Well, one of the definitions, I should say. It's very closely related to the gamma function, so I'm just gonna, they could have been grouped together in this situation, but honestly, there are lots of situations where you're going to use the digamma function without the gamma function, or the gamma function without the digamma function. I will also put the first polygamma function, with a little 1 up here. And this one also doesn't really show up that often, but I decided to include it just as a sort of honorable mention here. So for these ones, they only really show up when they're used in tandem with infinite series or when you're using the gamma function, and for that reason I'm going to have to also give these a B tier, because again, you have to rely on other integration methods in order to use these. However, they are an essential tool also, so again, sort of rather than an integration method, these are more oriented as a sort of tool that you're going to use while you're using a different method. But, absolutely essential for lots of different types of integrals, but again, not every single integral out there. So for that reason, I'm going to give it a B tier. Also, because whenever you're using the gamma function, or the digamma function, you have to know a lot about it. So you have to study the digamma function, you have to know the identities. You can't just go ahead and hop in and say, oh, this is super simple and straightforward and it's really intuitive. You have to work with them for a few weeks or months before you can just see, oh, this is going to look like a digamma function. So for that reason, it's going into the B tier because it's a little bit difficult to use. All right, well, now we're going to have our first C tier, very sadly. And this isn't even because the integration method is that bad. We're talking about the Weierstrass substitution. which is t equals tangent of x over 2, also known as the tangent half-angle substitution. And you may be thinking, well, why are we using this wacky substitution? The reason for this is when we make the substitution, sine of x is going to be equal to 2t over 1 plus t squared, and cosine of x is going to be equal to 1 minus t squared over 1 plus t squared. So whenever we have a rational function with sine of x and cosine of x, we can just make the tangent half-angle substitution, and it turns into a rational integral, which we know is always going to be solvable, even if it's going to have some very difficult to figure out terms. So the reason that I'm including this as a C tier, even though it's almost an essential tool, because actually, surprisingly, in general, when you're using the tangent half angle, there are other ways to solve the problem. It's just a handy little shortcut, and it doesn't really cut off that much. I mean, obviously, it's something that all of you want to know because it's going to help with those integrals, but again, it's a little bit of a shortcut that isn't necessarily necessary, and also it only applies to trigonometric integrals with rational functions of sine of x and cosine of x, which is so hyper-specific that it doesn't really apply to a large class of integrals. Still, something good to have in your back pocket. Double or multiple integration. So this is when we're doing an integral and we decide to convert something else into an integral. So it's going to look something like the integral from the integral of f of x comma y dx dy. Now, obviously, this is going to have quite a few different applications across different types of integrals. It gets especially nice when we have something that can really easily, we can use the Jacobian on it, or we can even make a polar substitution, right? So there's a lot of different ways to play around with these types of things. In general, I end up using this a lot in situations where you can also use Feynman integration. So they're sort of interchangeable because in a way, when you write something as an integral, that's the same as differentiating it and then integrating it again. But personally, I prefer this a little bit more because it's just a lot easier to work with without having to like solve for the constant of integration or anything like that. So I personally prefer this a little bit. However, I'm going to give it a B tier just because its ease of use is a little bit less for newer integrators than Feynman integration. However, absolutely, multiple integration is something that you should totally learn. Obviously, you learn it in multivariable calc if you're going to take that, but multiple integration, yeah, absolutely something you should learn in order to solve all sorts of integrals. So B tier for this one. So next up, we have a bit of an odd one. And this one, I'm not really sure of what to call it. I saw it on one channel called Mathematics My, which absolutely you guys should check out. They have some crazy integrals and infinite sums on there. But basically the statement is that if we have the integral from 0 to infinity of f of x g of x dx, it's very, very easy to show that this is the same as the integral from 0 to infinity of the Laplace transform of f of x times the inverse Laplace transform of g of x. And this may seem kind of niche, and in truth it is a little bit niche, but the main use when we get something like this is if we have anything, so we have to take the Laplace transform of one thing and the inverse Laplace transform of something else. So if we have some like polynomial, or we have some like rational function, those are really, really easy to, or I guess, no, not polynomial. If we have some rational function, those are really, really easy to take the inverse Laplace transform of. And then if we have some, say, some sinusoidal or trigonometric terms or some exponentials or stuff like that, those are really easy to take the Laplace transform of. So like sine of x times e to the negative x, right? This is going to be nasty to deal with, but using this trick and in combination with other tricks, you're going to be able to really easily evaluate some integrals that should be really tough. So just using, this is really easy to take the Laplace transform of. This is really easy to take the inverse Laplace transform of. So you're going to have a lot of different opportunities to figure out something that's going to work with that. So yeah, definitely one of my favorite tricks that's not very well known. So one example of where you could use this is the Borwein integrals, which is essentially like integral from 0 to infinity of sine of x over x times sine of x over 3 over x over 3, and then you continue with the odd numbers like that. And it's really easy once you expand out all the sine terms to just take the Laplace transform and the inverse Laplace, and it becomes just a simple rational like arctangent integral. So again, absolutely very, very, very incredibly useful tool, but it's a little bit niche, so for that reason I'm going to put it in B tier, because again, there's a lot of integrals you can apply it to, but it's not one of those universal methods like power series or Feynman integration or contour integration. All right, next up we have King's property. So King's property is, honestly, it's kind of debatable whether it should be included on this list because it's a completely elementary method. It requires no knowledge above, like, honestly, first month calc. This is something you learn in like Calc AB in the first week of the first semester. We have integral from a to b of f of x dx equals integral from a to b of f of a plus b minus x dx. And something else I'm going to include here is the integral from 0 to infinity of f of x dx equals integral from 0 to infinity of 1 over x squared times f of 1 over x dx. And this doesn't really look like the same thing, but when you're playing around with King's property and also this same substitution, you'll actually find out that often King's property and this same substitution right here are going to have the exact same effect on certain functions like natural log of e to the x, or natural log of x, and rational functions. So that's actually really interesting. But the reason I'm including this on the advanced integration method is because it shows up everywhere, on everything from integrals with sine to rational integrals to all sorts of different things. Probably its most important use is with sine and cosine or with rational integrals, but this just pops up so much and it's so incredibly powerful that it can reduce stuff that looks like a monster if you're not familiar with it to something absolutely very, very easy. So for that reason, I'm going to have to actually put this in S tier because I just think it's that good. It's such an amazing integration method. Absolutely have to know this if you want to be solving integrals. And now we are getting to the worst of them all. Fourier series. We have f of x equals the sum from n equals 0 to infinity of what is it? An cosine of nx plus bn sine of x, sine of nx. Absolute D tier, obviously. Useless integration method, has no application to anything. Of course, those of you who watch my channel know I'm just joking. I have a bit of a thing against Fourier series. It's really not very well founded. I just don't like them. I don't like using them. I don't like having to use them. I would absolutely prefer to use anything else. So for that reason, I'm giving it a D tier. In all honesty, they do have an application to lots of different integrals, not nearly as many as the Laplace transform or other important integration methods, but the Fourier series are probably a good thing to have on hand. However, just for me personally, I'm going to have to give it a D tier. And it's going to be alone down there because I just really don't like Fourier series. I'll take any other method over Fourier series. So this one's actually pretty fun. We have the Lobachevsky formula, or Lobachevsky's integral formulas. And if you haven't heard of that and you watch my channel, it's because I've actually never used it on my channel. I just haven't found a problem that I think has a really unique answer with Lobachevsky's formula. However, it is overall a very useful integration method. Again, it's just not something that I've covered in any videos yet. So the statement is the integral from 0 to infinity of sine squared of x over x squared f of x dx equals the integral from 0 to infinity of sine x over x times f of x dx equals the integral from 0 to pi over 2 of f of x dx, as long as f of x plus pi equals f of x and f of pi minus x equals f of x, I believe. So essentially, f of x is some sort of trigonometric expression, right? Trigonometric function. It's very, very, very niche integration formula. Obviously, when it does show up, it's going to be incredibly helpful and useful. But I'm just going to have to say, because it's so niche, like there's only a few different situations where you're actually ever going to use this. So for that reason, I'm going to have to put it down in C tier. But, it's a good thing to have in mind if you see something that's sine squared of x over x squared times some monster trig function. you might want to check and see if it satisfies these conditions. And it's always something to have in your back pocket. I've used it on a couple integrals. I haven't found them video worthy just because it's essentially just apply Lobachevsky's formula once and then it all just disappears. So good thing to have on hand, especially if you're going to go into some integration B or something like that. And we are in the home stretch. We have just one integration method left, and this one is a little bit interesting. This one is just in general using complex numbers. So this is excluding contour integration because that's, I feel like, a separate integration method, but this is any situation where you're going to ix complex numbers without using contour integration. So for example, rewriting sine of x as e to the ix minus e to the negative ix over 2I, or I don't know, I suppose that's the main method, but there's some things that you can do with natural logs and some other situations. Overall, this is a very, very broad topic that I'm covering here. It's not something that actually gets used too commonly, but I would have to say it's definitely an important integration method to have in mind. So I'm going to give it A tier because it just has applications to all sorts of different integrals. Once you add in contour integration, that like triples the amount of integrals that it applies to, but complex numbers by themselves are just the right way to start thinking about things. Like something you should always do when you see an integral is if it has a complex form to write it, and I don't mean complex by like more difficult to understand, but I mean complex as in complex numbers, it's probably better to write it in terms of complex numbers just because that's the natural way that numbers work, right? Complex numbers are real in the literal sense. So that is the last integration method for today, so let's just go ahead and look at the tier list. Alright, so this is the cumulative list of the tier list right here. You'll notice that there's a lot more closer to the top and the middle than there is on the bottom. That's because, let's be honest, I only picked integration methods that I liked. So even the stuff down in C tier are things that are integration methods that I absolutely love. And I think if there's anything on this list that you don't recognize, especially if it's close to the top, you should absolutely take a moment, look it up, learn how to use it, see some examples, and keep it in your back pocket because these integration methods are really the ones that are going to come in most handy overall when you're doing those sorts of integrals from integration Bs and the sort like that. So to sum it all up, we have in S tier, Laplace transform, infinite series, contour integrals, and King's property. Those are the big guns. In A tier, we have our more specific cases like Ramanujan's master theorem and Glasser's master theorem, as well as our more general tools like Feynman integration and complex numbers. In B tier, we have our more general, a few more general tools like beta and gamma functions, as well as the digamma and polygamma functions, and stuff like the Mellin transform, and then some stuff that's more for specific situations like double and triple integrals and the Maus identity. Finally, in C tier, we have our trig-specific methods that are only going to work on a few different sorts of integrals, which are the Lobachevsky formula and the Weierstrass substitution. And on the bottom, we have the worst integration method of all time, which nobody should ever use, Fourier series. So I hope you guys enjoyed this video. I know it was pretty long, but I really hope you watched it through. Again, thanks so much for 1,000 subscribers. 1,000 subscribers. All this support has been absolutely amazing, and I just love making videos for you guys. I want to keep doing this, and thank you. Really couldn't have done it without you guys. And yeah, if you want to keep seeing more videos, please let me know if you have any suggestions. If you want to see videos on any of these methods, please drop them down in the comments. So yeah, hope you guys enjoyed the video, and I'll see you next time.